Good afternoon to everyone, and welcome to the first Portness webinar. Today we're going to talk about cable and CPS fatigue and ultimately failure. Today's speaker or presenter is Henrik Bang-Andreasen. He obviously needs no introduction to this industry, with more than 4 decades in the industry, as well as more than 50 involvements with offshore wind projects. There are a few housekeeping items for this presentation. The first is that this presentation, it will be recorded. There will be a Q&A at the very end of this webinar, and you can either submit your question in the chat box or send me an email at ole@portness.uk. And Henrik, why don't you take us away from here?
Yep. There we are. So this deep dive is present my perception of the situation from working within the industry for this time with cable protection interfaces for this period. Well, I'm first going to start with a very short introduction to offshore wind. It's not going to take a long time in this presentation, but just for those who are not familiar with this, each turbine is connected to the offshore substation via a string of inter-array cables. Today they are 66 kV, they were in the start 33 kV, and they will very soon become 132 kV cable. And then these cables are with typical offshore substations, then via export cables, either connected to onshore or via DC converter stations through DC high voltage onto onshore systems. The actual setup and the protection of the cable is predominantly by burial of the cables. So most of the cables are buried in the wind parks today. There's a few wind parks where it isn't, but this is the norm, that the cables are buried in the seabed. But unfortunately, they have to come up to the foundations, close to the foundation. And what you will see here in this presentation here, or this picture here in the bottom, you will see that these actually scour out of the seabed and into the foundations. And as you see on the top picture here, you can see the same situation made on a test onshore. So the issue is that the cable is predominantly protected under the sea, and the cable is, for a short section, actually exposed to dynamics inside the cable protection system where it exits the seabed. And this is one of the reasons why we are having some issues, and this is a lot about the focus in this presentation. Just to have mentioned it, floating wind is, of course, a lot of people talk about it. We don't have much floating offshore wind. The biggest offshore floating wind park is actually an electrification or part electrification of a Norwegian oil field. So we there have 11 turbines of a spar type, as seen on this picture here. But again, it's a similar system where strings of inter-array cables of 66 kV for this particular park is connected together. And of course, I assume that it will be the same 132 kV with the larger turbines. But the thing that we don't know yet is, because there isn't a standard yet, is what will be the dominant layout for the cables for the floating wind parks, especially not in what will be called shallow water floating, because what is too deep for fixed foundation will maybe very shallow for floating wind. And With that, of the general presentation, I'm going to talk about a little bit about CPS failures. And the first thing that I'm going to just talk about is there a trend and has root causes being managed and so. And there are some trends. And this figure here that's published by OIE Catapult, the electrode program in the UK, basically is supported by the information here that we put in with C-Cube stating in 2021 that they claim, and that is for resolved claims from the year 2020, that the typical failure is about pound 1.7 million in the period from 2010 to 2015, and it more than doubled to 3.1 million pounds in 2020. Also, the total cost of failures is going up from 124 million pounds in 2015 to 500 million pounds in 2020. So obviously it's a concerning thing. But one of the things that I wanted to use this slide for was that here you can see that consolidated 92%, the 46% from installation, the 15% from faults in cable design, and the 31% from manufacturing issues or failure causes. In obviously 2020 resolved unit that was reported in 2021. If we go to the next year in 2022, which covers what happened in 2021, those failures that were 92% are now reduced to 21%. So if we're looking for some positive trends, yes, people are actually tackling some obvious issues. The big unknown here is, of course, that there's a 63% unknown failures of these cases, and when this is resolved, insurance claims, this lags several years behind what's actually going on. So the data that we see in 1 year here presented in 22 for the year 2021 may actually represent things that have actually 2 or 3 years on them before they come there. So we lack, and that I want to stress here, there's no good statistic. There's no industry statistics. We can't go in one place where we can know absolutely all failures and root causes, and so that's not a public public figure. In 2021, a big issue came out about one particular owner-operator needed to stabilize a number of their cable systems. And I want to speak a little bit about this, the reason for stabilization, just for you that you get to know this. I'm excused for this a little bit blurred figure here, but what you have in the background is you have a blue structure, which is here a monopile. You have the cable protection system, obviously with the cable inside, as the green figure with the red towards the foundation and going into the brown seabed below it. And this is curved out to one side. And the reason why one wants to stabilize is that some people believe that, just to take that away, the cable protection system doesn't stop the movement. The cable protection system is intended to reduce the movement so that the cable is actually only being moved within what will actually lead to sufficient fatigue life of the cable. So this, what you see here curved out to one side, is a cyclic movement that in the next moment it will be cycled out to the other side. So this cycling from side to side is obviously an issue. And one of the cases, or one of the reasons why one wanted to stabilize these systems, was obviously that the system, now you see the same figure here. So this curve that you see here, where we're looking from the seabed end, here we look from the side. So here you have the seabed end on the right-hand side of the lower set. That's a dark green. And you have the foundation in the gray part on the top of the three curves in the bottom. So just, it's not a complete different curve. It's just that this is seen from the different side with some lift. And I have imposed a CPS system on top of it, just to give you an idea that the CPS system have a latch system into the either the aperture of a monopile or into a bell mount of a J-tube. And then there's a bend stiffener and various other sections out of the CPS system. And this is under dynamics for the orange section for the CPS. The cable is under dynamic operation under the entire length that is covered by the two orange and also the step between. Tension of the CPS is the red stripe. So there you have dynamic, which is bending, curvaturing, and the red is tension. And those are the two, primarily the two things that the analyst is basically go in and evaluate whether you have a certain curvature and a certain tension to the cable that then can be translated into some kind of predicted fatigue life of the cable. There's a gray curve which shows the non-metallic fatigue, which is basically abrasion and other like creep and other things that is in non-metallic materials. And you have, for the black stripe, is basically the metallic, which is corrosion and abrasion. And so the idea then, and the reason for the stabilization, is that this curving forward and back, and here showing in and out of the picture, that we see is actually can be reduced if one stabilize. So basically one weigh down the CPS and cable somewhere on this curvature, and basically under this ballast, which is weight, and that's the stabilization, the CPS and cable no longer moves, and therefore one reduces the mobility or the movement of the CPS and the cable inside. I've just imposed the same figure here, or the same illustration of the three curves seen from the same side here. So you can see the idea here is that we basically come from that we have a very long section here of mobility to a much shorter section of mobility. The other issue that's very interesting is whether the near seabed conditions are well understood and whether they are well modeled. And in the figures that I presented from you before, they are basically from the conventional software program that is not able to do current amplification, which happens around the foundation. So here you see a picture or a table of a setup where you have various depth, 20 meters, 40 meter, and 60 meter water depth, and you basically have full ocean blown, which is exposed. And here it's just shown that this is in the US, Asia Pacific, and Europe zone, and you have, which is in the blue colors, and you have shielded, where the shielding means that it's not exposed to the full ocean swell, which means that basically the wave period time and the maximum wave height is somewhat reduced. It's not necessarily benign waters, but compared to the full exposed areas, it's actually helped somewhat. And you can see that on the figure that the on seabed meter per second movements is reduced in these shielded areas. I have highlighted one particular figure here at 40 meters, which is 2.4 meter per second. So what this what this table here, basically using this analysis and those assumptions that lies behind this table, one had assumed that with the current amplification factors, one end up with an absolute maximum current 1 meter above the seabed where the CPS is of 2.4 meter per second. If one take this the very same mid-ocean data at the same depth and put that into a CFD analysis with an GSS turbulence model, one come to some radical more higher velocities. So one goes from this 2.4 meter per second or 2.56 meter per second if we go to 36, 37 meters or something, now becomes something on the other side of 6 meter per second in the area where the CPS is, and certainly where the also the stabilized CPS is. So what happens is when the wave basically passes from one side of the foundation to the other side of the foundation is shown on the two pictures out on the right. On the top hand side, you can see the front of the wave basically entering into the wave, and you've got the current of the wave going this way around. And when the wave basically passes the monopile, you have the rear of the wave creating a similar not exactly the same value, but a similar current, but in the opposite direction. And this is the reason why we get this cyclic, why we are talking about cyclic, and unfortunately cyclic with waves, not cyclic with tide shift or something. So this is something that is happening with ever the wave period time. So at a much higher frequency than for example tidal, and so would assume. Last, this impressive figure that I have borrowed from Aurora, which is part of the University of Western Australia that have worked a lot on this, where they actually demonstrate what is it that happens. And what happens is that we got a rolling vortices. So around a foundation, whether that's a monopile or to a slightly lesser degree if it's a lattice or jacket construction that rolls around the obstruction that the foundation actually is to the wave, you get these vortices around the system. And you see here in the bottom of this area here, you see this looks like this quite a turbulent area, and this is obviously what is building the horseshoe hole. So if one doesn't use scar protection, this is where the scar holes will be. But the problem is this is also where we have the CPS and the cable, and therefore quite problematic for us. The problem here is, of course, or I was going to say, the excuse is that we did not have that computing power. Before 2016, we didn't know much about the current application factors. Maybe we should have known about it, but it was not published before then. The current application factors was not introduced into the analysis until probably around 2020. And this kind of information that you see in front of you most likely will be more published in the year to come. But they are very similar to the information that you get from CFD. Obviously, if we speak to Aurora, and they will say this will give a more precise thing. The thing is that the currents, accelerated water currents that impacts our CPS parts and cable parts that is not under stabilization under the seabed close to the foundation are much more severe than the analysis basically have been made for. Then there's another sector, and here we have the same picture again on the right hand side with the curve. So this is the curve that goes from back, and basically I was just going to talk a little bit how do one actually get to this curvature, because there's a software program that basically helps people doing this, but they have to set up a model in the program, and with the model one have to set up a number of assumptions. So both in setting up the model and the assumptions going into the model actually allows for trimming. So one could say it's not that there is one particular way of doing it. And here I have on the left hand side, I just have the one of the modal issues is where the cable actually, or the CPS, enters the seabed or comes out of the seabed, depends how you look at it, where the modal then sets up a sleeve, and the sleeve is then surrounded by what is called a coil spring, set of coil springs, where the coils closest to where the CPS is protruding or exits the seabed, they have the weakest force, and as you get further and further into the seabed, these springs are stronger and stronger, and in this way you basically construct in the model here, you basically tell the seabed to act as a bending stiffener, which is of course very optimistic. There may be some good reasons why in some cases the seabed will help that, and there may be some other reasons where the seabed will not do this. But what I'm saying here is this is assumptions, and not that it's not actually as built data that lies behind this. This is projected data before the construction of the wind park starts, and therefore, to some degree, assumptions that is not fully accounted for. But yet again, also I expect that one can say, well, they're not totally unrealistic, but my assumption is that, again, an assumption is that they are neither a correct stipulation of any of the positions. That curvature is then being used to form in the program, in the software, is then being used to set up a set which is predominantly what the owners operators want. They want to know how long time will our cable survive with the CPS under these conditions. And this is what you see on the right hand side. Here's the 7 different cables with conductor, screen, and armor wire. And with the number of curvature and tension parameters that is then applied to it, the analysis then comes out with a number of figures. And if you look at the lowest range here, we have a 1,000 square millimeter aluminum, copper cable, and the screen of that copper cable actually has a 26.5 year calculated fatigue life. That's with a safety factor of 10. So really, when you run the analysis, it says that it will take 265 years before there's a high likelihood or that the screen will actually break. But the thing is, and here you see the conductor here is 2.54 years in the power of 10, and the armor wire is in the power of 31st. So you can say that principally this should work a long time, and that's of course one of the issues that all the failures that happens on CPSs and cables. That's basically analysis indicating that there should be no problem during the operational life of the wind park. The last thing that one does with how one actually get to these calculated fatigue issues is that one does not go to the cable manufacturer, because the cable manufacturer sells a static cable, and the static cable, the cable manufacturer says, okay, you can bend this cable a certain number of times. You can bend it when you load it out, when you maybe retransport it. You may you have the cable lay facility. You may repair it, so you may pick it up 1 or 2 times. But it's a cable that's predominantly made to be buried into the seabed. So what one does is one actually left off from the cable data sheet the size of, for example, the conductor. And if this is an aluminum conductor, one goes into the aluminum conductor. So for one of the aluminum conductors here, we have 4 different aluminum conductor. One actually go in and say, well, with the curvature, with the tension applied to this, and how the model actually set up and find out how much tension any one of the components inside the cable actually have is, of course, another assumption and model setup. But then one come out and say, well, okay, if we have so much load in total, and we then assume so much of the load will be on this conductor. We then go into an engineering table, find the SN curve for aluminum conductor, and we use that as the thing. So it's not the cable design, so it's not being tested, and it's not being verified or qualified or guaranteed by the cable suppliers. So this is again an assumed value. So this is leading to why I actually believe that the cable stabilization is not necessarily a way to stop cable fatigue, because the cable fatigue that happens inside the cable, the thing that is being calculated for the fatigue life of the cable is based on that you have a constant curvature. So when you have a curvature, you say in the middle of the curve, you have the highest curvature, and then to each side of the curvature gets less and less. So you basically have a quite benign transaction between what's being curved and what's not being curved. This is in the models. This is basically, if you look at the upper right hand side of this picture, you got the cable here, and if this cable is being bent, this is shown by this structure here is being bent, then what's on the outside of the bent radius is being tensioned. What's on the inside of this bent tension is basically being compressed, and then the cable design then have to allow some kind of slip so that the unit that's under tension and the unit that's under compression can sort of equalize these. And what you see if you cut a cable over and you bend the cable close to the end, you can see that the various big components of the cable will basically protrude out at a different length out of the cable when you bend it. This is a known issue for all terminations of cables, and this is the reason why you typically have a kind of a termination system. So the big issue here is that we get back to that having the cable pinned, the components of the cable pinned under the stabilization weight, and you have the part of the CPS moving next to it, we actually have an issue in this interface, not because of the rock berm, but because the rock berm actually pin down the cable inside and moves next to. Okay, I saw that I was going to say before I take the questions, just very short. The near seabed, the conclusion is that the near seabed conditions are poorly understood and poorly modeled, I believe, at least in the models that are being used for predicting the life expectancy of the cables and CPS systems. The accelerated water velocities working on the CPS and on the cable, which is actually bending the cable, is a factor of magnitude greater than assumed in the analysis. Therefore, the also stabilized or not, the movement in that section that's not under the rock berm is more mobile. The analysis, as I told you, is a bit biased, and I believe that the ballast stabilization increase the fatigue, as I told you about this problem that it is being pinned down under. Okay.
Perfect. There's actually two questions, and I think we'll take them in reverse. So the last one was on this slide, I believe. So the question is to confirm this is with the cable perpendicular to current and more conservative than cable entry in line with current. I'm not sure if you can see the question.
That's of course correct. If you look at the typical conundrum have been that you have to take the worst case, and therefore if you, for example, and this is the reason why in many wind parks, if you have problems with reaching the fatigue life of the cables, one is actually looking at then one actually look at the which wave directions and so is, because the issue is that typically one have to assume that the longest free span and the waves coming perpendicular to this, which is worst conditions. This is a correct assumption what is being asked here, that often yes, principally the DNV ask for that, that you have to use the conservative system in this, but it doesn't really help being conservative about something which is what I state, or my perception of this is that it may already have been overly optimistic in the first place, and then being conservative about it may not really help it, and that's of course the reason why we see cables that are typically now having over the board range around 6 years in operation, and they're supposed to live for more than 30 years, and we already have issues with the cables.
And then there was one more question to slide 15, asking, is this worse on flat seabed with presumably more laminar flow than one with sand waves, which is presumably more turbulent?
No, actually the mobile seabed sand waves, ripples, or whatever you have will give you another issue. And obviously, if you have if the sand wave reduces the water depth a lot, you can say that the current on top of the the sand wave will obviously be higher than if the sand ripple or sand wave wasn't there. But it's the currents are basically generated around the foundation, and it has nothing to do with what the so to speak the seabed around it looks like. It has an effect on the seabed around, because if you have low shear strength materials or highly erosive seabeds, you will see, like you see in some areas like in South China Sea around Taiwan and so, where you will see very excessive scouring 20-30 meters away from the foundations because of the low viscosity or low shear strength of the upper materials. But the actual currents around the foundation is not impacted by the sand ripples others than, as you saw with the table, is obviously if the sand ripple is 20 meter deep and suddenly you have 20 meter deeper, obviously the current at the top of that sand or on the 40 meter will be much less than if it was only 20 meter water depth.
And then there's one more question maybe I will take. So if we're working on a new commercial solution, yes, it's no secret that we are working currently testing a product. We're actually a full system solution that will tackle this. And we will come back with timelines. And for you guys that are interested, I would encourage you to just follow our LinkedIn page and follow us on our website. And then I think before we answer the next question, we hope to have 2 more of these webinars. So we hope to host one December 18th, where we'll talk you and walk you through some of the environmental impacts from this problem. And then to the most recent question here, are we planning on retrofitting only or new installation as well? We hope in January to have a similar webinar to today, where we will walk you through how our product works and how it integrates into the offshore wind industry. So we'll get back to you with an exact date there and more information. But again, we will keep posting things on our LinkedIn page. So please just keep an eye on what we publish. I think that's all the questions, Henrik. Can you maybe just in 30 seconds just try to summarize kind of the whole presentation in the end here?
Yeah, again, that's very much the takeaway is very much the conclusion that because we have not understood the near seabed conditions well, and we model it poorly, because of that, the water, the accelerated water particle currents are impacting the equipment. So the CPS and the cable down at the seabed close to the foundation, much more than one has accounted for. The analysis are basically biased, for example, thinking that the CPS is full of water and other things. There's a lot of those issues that basically comes true, that say, well, there is a reason why we are seeing failures, while the analysis basically predicted that we are not going to see any problems with these cables, with these CPSs for the next 32 years until we are going to demobilize the wind parks. And at last, the thing is that the stabilization, as I say, is what I say is basically my worry here is that a very well-established understanding in termination technology is not really applied to the stabilization. Yes, remove one particular problem, and unfortunately, I believe one basically generates an even greater fatigue issue with the cables.
Perfect. That was a little bit extended 30 seconds, but that's good.
Sorry.
Guys, thank you so much for your time. If you have any questions, please reach out to Henrik or myself. And here you can see Henrik's email. And then we will get back to you with another webinar in December on the environmental impact of CPS and cable fatigue and failure. And then back in January on the product we hope to show to you in January. Thank you so much for your time, and have a good weekend when you get there.
Yeah.
Bye-bye.
Thank you for listening in. Thank you. Thank you for the questions.